to start trying to catch up to you. So I was a little nice on this first one, but not terribly. A little question marks, obviously. I want to get that side. Did anybody get this side figured out?
Yeah, 17.
17, I love it. So some of you guys know 3, 4, 5. There's also 8, 15, 17. I mean, there's a lot of those that work. And what do I mean by that? If you just draw an arbitrary right triangle, it's almost definitely going to have a gross side somewhere, at least one, some square root side, right? There are certain numbers that actually go nicely together in a triangle. 8, 15, 17 is one of them. So let's see, what's the sign? Is the angle in the base?
Yes. Yeah.
Does everybody understand what I mean by that? Right?
Yeah.
It's related to the base, I love it. So sine would be
8 over 17.
8 over 17. So I'm like to know what cosecant would be.
Cosecant is 17 over 8.
Gas. Cosine.
17 over 17.
Yeah, it's the x side. So secant's going to be
17 over 15.
yeah. Tangent
8 over 15.
8 over 15. Cotangent
15 over
15 over 8. Very quickly. We already talked about this before. What's the biggest sine can be?
1.
1. I love it. Be really weird. It would be basically a triangle that I smush, right? It would actually be this way. So it's all y, so the sine would be everything. So that would be 1. And you can see it from the ratio. The hypotenuse is always the biggest one, and it's the side divided by hypotenuse. The biggest sine could possibly be is 1. Cosecant is the reciprocal of that. So what is the smallest cosecant can be?
1.
Positive. Yeah, 1. And then it goes to infinity. Okay, crazy shit. So we'll see that when we start graphing these suckers. We're not quite there yet. The rest of these work basically the same way. This one, 3, 5, what did you guys get for this side? I think we had exactly this triangle earlier, just about. Root 34, right?
Yeah.
So then the only thing you have to be careful about is rationalizing in the right places. So what's sine going to be?
3 rad 34 over 30.
Well, let's see. Sine. So the base is here, right? So then I'm going to do this. So now 3 is my y side. Good. Let me make sure you guys all are with me. That's the one thing SOHCAHTOA does better, and it does it better by this much. Because all I have to do is turn. How do I know I have to turn the triangle?
The angle's not
Angle's down the base. Now the angle's in the base. So what's this? This is the y side. So let me just say this is y, and this is x. Relative to the angle, this is like the y-axis is the x-axis because it wants to be like this. You guys with me? Maybe. So the sine would be y over x. I'm sorry, y over the hypotenuse. And then you have to rationalize that. Cosine,
5 rad 34.
5 over rad 34. So when you rationalize that,
Um,
is everybody with me?
I just have a quick question.
Yeah.
So we don't rationalize the square root of 34 before putting it where the hypotenuse is?
Oh, I can't. So rationalization means making the denominator rational.
Okay.
This is just a number. I can't do anything to it. The poor little dude is square root of 34.
Okay.
I can't do anything to that, right? It's going to be irrational no matter what I try to do to it. It's just going to be irrational. I'm not allowed to square it. I'm not allowed to do anything to it to change it. I can't change the number, right? In a fraction, I can multiply and make the bottom nice. And what does that mean? The top gets bad, right? Relatively, yeah. You guys all with me? We radicals suck already. They're even worse when I divide by them. Tangent's going to be nice, though.
3 over
I
5,
thought.
right?
3 over 5. And of course, cosecant would just be
5.
cosecant.
Oh, square root of 34
Yeah, root 34 over
over
3.
Yeah.
Secant, root 34 over 5. And cotangent,
5
5 over 3. You just got to flip the first 3. So you really just have to memorize 3 trig functions. And then the other ones are just the flips. You got to memorize that sine goes to cosecant, right? That kind of thing. You guys doing okay so far?
Yeah.
All right. So once you've done a couple of these, it's always the same. It's crazy. So now the angle's back in the base, thankfully, right? What's this? 8, what's it? 9, 13. So who got this side?
2 rad 22.
Yeah, so it'll be 13 squared minus 9 squared. Why is it minus? Because that's the hypotenuse. Right? Is everybody with me?
Yeah.
So if I subtract one of the sides squared, I'll get the other side squared. So then I get, what is that, 88?
Yeah.
B squared is 88, so when I take a square root, now here's the other thing you have to be able to do. When I take the square root of 88, how do I simplify that? I don't know what the hell the square root of 88 is. I can estimate it, but I don't know what the hell it is. But we can simplify it. So what do I do?
Or you can find whatever number.
Yeah, what's a square number that goes into 88? Because I can do the square root of a square. So it'll be square root of 4 times square root of 22. 2 rad 22. I like it. So this is 2 rad 22.
Could you do 9 rad 7?
9 rad 7. How do you mean?
Because you would have 81 times 7.
For which part? Oh, I see what you did. Alright, so let's be careful. Okay. Square root of 88, I agree, is the square root of 81 plus 7, correct? Plus. What are square roots based on? What operation are square roots based on? Multiplication. Can they distribute across addition then? No. You guys with me? Are you guys with me? Very quick, just go with me for a second. What is a coefficient based on? If I have a coefficient in front of x, what does that really mean? Don't say 2 times x. What is it really? 2x is doing what?
Multiplying 2.
What would 2x's multiplying be? What's x times x? It's not 2x, it's x squared, right? Exponents based on multiplication. What are coefficients based on? What are these 2x's doing to each other? X plus x, yes?
Yes.
You with me? I don't know, but you're all like, yes. So watch this. Do coefficients distribute across addition? Of course they do, because coefficients are based on addition. Are you with me? So this would be 2x plus 14. You all know that shit, right? That's the good old distribution property, right? Do powers distribute across addition? Hell no. They're based on multiplication. They do not play well with addition. This is not x squared plus 49. Does anyone know how you would do this? You have to write it twice, and you have to FOIL it. I love it. Better than FOIL. You have to repeated distribution, right? So you would get a middle term, correct? You guys see what I'm saying? So this is something that people make mistakes with really easily, but exponents are based on multiplication. Now, real quick, square root of x. That is an exponent. Because what does square root do to something? It cuts it in multiplicative degrees, right? Multiplicative degrees? Sure, Jeff. So this is another way to write square root of x is x to the 1/2 power. Because what's a power based on? Multiplication. So a 1/2 based on multiplication cuts something in half multiplicatively. I don't know if you guys are with me or not. Because trust me, Math 285, I teach here. I will get somebody tell me that the square root of x squared plus 9 is x plus 3. What mistake did they make?
Addition.
Does the square root distribute across addition? No, because it's a power. No, I can't do shit with that, right?
Yeah.
Okay, I like it.
Although, for that problem, wouldn't the square root cancel out the x squared though?
No, because x squared
It
plus 9.
would if only there was an x squared in there. I'm going to blow your minds. Is there an x squared inside the square root? Nope. There's an x squared plus 9. Do you know what number that is? I have no idea what number that is.
Yeah.
Are you with me?
Yeah.
So I have no idea if I can square root it or not. If I had the square root of 9x squared, I could do stuff. Yes?
Yeah.
Because the square root works with multiplication. What's the square root of 9? 3. Let me blow your mind even more. Holy shit, Jeff. What's the square root of x squared?
X.
No. Ha! Sorry. It's the absolute value of x. Did you guys know that?
Oh, okay.
Help me out. What could x be? Give me a number x could be. Let's just look at square root of x squared by itself real quick. What could x be? Give me a number x could be. 2. Alright, so if x is 2, this is the square root of 4, which is 2, correct?
Yeah.
What else could x be?
Negative
-2.
-2. All right, if I make x -2, no, it's not. What's -2 squared?
Or,
Right, and this is x equals -2, correct? That's how we got there, yes? Square root of 4 is what? 2. So is the square root of x squared equal to x? Remember, x was -2 here, correct?
Yes.
Is the square root of x squared equal to x?
no.
No, it's equal to the absolute value of x. Yes?
Okay.
Thanks for that, Jeff. That was brilliant. So, yes?
Well, rad 4 could also be negative 2. And then it
Hell no. No. So if I say, what do you square to get 4? What are the two answers?
would be negative 2.
2 and
-2 and 2. Because it's the square root of 4 and then negative square root of 4. When I say what is the square root of 4, what's the sign in front of it? Plus. So I'm saying I want the positive root. So when you see a square root symbol already written, they're telling you which root they want. Does everybody understand there's 2 square roots of 9? There's 2 roots of 9. There's -3 and 3. But if I say what is the negative square root of 9, that is -3. That I want the negative root. If I see the square root of 9, I want the positive root. We went off on a major tangent there, but okay. These are little things that will pop up every now and again. They just will. Does anyone remember any of this stuff? Don't freak out too much. Not yet. All right, where did I my paper there? There. All right. So what about who remembers the? Did I finish that? No, I didn't. So now, is everybody cool with that? I mean, we do the same thing, don't we? What would sine be, for example? Sine A.
2 rad 22 over 13.
Yeah, 2 rad 22 over 13. Are you with me? So in this case, sine and cosine are all good. It's actually some of the other ones you have to rationalize. Because now that is in the numerator of sine and sine, for example, right? Cosine's definitely cool. Cotangent's going to have some issues. I'm going to have to rationalize it. Do you guys see that? Are you guys okay? Once you figure out all 3 sides, trig functions are easy. You just make the correct ratio after that, right? Okay. So let's do one example real quick from this triangle. What would cotangent be?
9 over 2. Actually, 9 rad 22 over 4 to 4. But you'd say
No, let's not go there yet. So cotangent would be x over y, right? So it'd be 9 over 2 rad 22. Let me write it down here so I have more room. Is the bottom rational? What do I multiply by to rationalize it?
rad 22.
Rad 22. So I get 9 rad 22 over 2 times 22, right? What did I put 20? So whenever there's a radical in the bottom of your expression, you need to take a moment and just multiply by it so that the bottom becomes nice and rational, yeah.
So how come it can't be like you multiply by 2 rad 22?
Because is 2 the problem?
No.
So why would I mess with it? He's cool. I need help with the rad 22. That's the one that's not rational. Okay. We took a lot of side notes in that. Focus on this. The other stuff is going to come up sometimes, so we'll talk about it more as it comes up. Give me the most basic Pythagorean trig identity. What am I drinking? Yes. Yes.
Sine squared theta plus cos squared theta equals r squared.
So real quick, let me kind of build that out a different way. I have a triangle.
Yeah.
Do you all agree with that x squared plus y squared equals r squared? Does everybody agree with me? What do I get when I divide by r squared? What is x over r?
Cosine.
As a trig, it's cosine.
Yeah.
Squared, right? What's y over r? Sine.
Sine.
What's r squared divided by r squared?
1.
Okay, so there's another whole way to get that identity. I kind of did that backwards to get it the other day, but does that make sense? So that's why it's not r squared, because you actually divide by r to make cosine and sine show up. Yeah. That is another reason why. All right, before I forget, that problem we did earlier, where it was it negative 5/3 x? Remember that problem we did earlier? Is it still up there?
Yeah.
Yeah, what's it right there?
Negative 5x.
5/3 x? Is
Yeah.
that- Okay.
Oh, yeah.
Just in case somebody's wondering why I picked what I did, I picked 3 for the input, right? And that made it go to here, and that was 5, and that was 3, -5, blah, 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 right? What if I would have put 6 in? If I put 6 in, 3 goes into 6 twice, that'd be -10. So this would have just been twice as big of a triangle. Wouldn't all the sides reduce to the same numbers we got?
Yeah.
So that's a beautiful example of the fact that I don't care how long these sides go, the angle doesn't change. If I had longer arms, this angle would be the same damn angle, right? If I do this, it's still the same angle, it's still the same angle. Still the same angle between them, right? Because these side ratios would just reduce to be the same thing. So it doesn't matter what points you graph when you graph those lines, it doesn't matter. It'll reduce to the right answer. Alright, what's another one that you get?
Tangent squared
Yeah.
theta plus 1 equals secant squared theta.
Kick ass. And the way to remember this is no quotient. You see that? Nothing's co. What's the other one?
Sine squared theta.
No, we already got that one. Careful.
Oh,
There's something with
1 plus
cotangent stuff.
cotangent
Yeah.
squared theta equals cosecant theta squared.
Yeah. So one has no cos, and the other one's exactly the same, but it's co. So it's tangent squared plus 1 equals secant squared, or cotangent squared plus 1 equals cosecant squared. That is the first evidence of why we called things co, right? Yes.
I just wanted to point out an observation that I just saw.
Sure.
In those equations.
Yeah.
The 1 seems to be moving to the left.
Yeah. Alright. Just because of the way that we created it, so
Yeah.
watch. So if I want to write this more symmetrically, I can have sine squared theta plus cosine squared theta equals 1. Tangent squared theta plus 1 equals secant squared theta. Cotangent squared theta plus 1 equals cosecant squared. Because of course I can add whatever order I want it,
Yeah.
right? Just to make sure you understand, this is a nicer way to kind of memorize it. And again, these are the first big 3 things. Besides the basic definitions of the trig function you gotta memorize, you gotta memorize these. Thank you, Jeff. Okay. So, somehow, I think this problem is gonna relate to these. And that's why I asked you for these right before this. I wanna know what cosine and tangent are if sine theta is this and theta is in the second quadrant. Real quick, if I'm in the second quadrant, what's true about cosine? Cosine likes
Cosine is negative x.
y, because cosine likes x, and in the second quadrant, x is negative, right? So that's beautiful, that helps. We already know where the negative y's and x's are. If you know sine likes y, sine is positive whenever y is positive. Cosine's positive whenever x is positive. So I already know cosine is going to be negative. What about tangent?
Tangent. Well, it's sine over cosine.
Beautiful.
over x.
Sine's positive, cosine's negative, tangent's going to be negative. Just keep that in mind. I'm going to show you 2 different ways to get this. Let's use these directly. If I want to know what cosine is, and I know sine already, which equation do I use? Which equation involves what I know and what I want to know? Which equation? I know sine, and I want to know cosine. So which equation am I going to use? The first one, of course, right? So what do I put here? What is sine theta? Yeah, square root of 11 over 5, and I square it, plus cosine squared equals 1, right? I'm just plugging in what I know. What do we do next?
Well, you square it.
Yeah, what's square root of 11 squared? 11. What's 5 squared?
25.
Holy shit. Sorry. Couple steps away now. I want to solve for cosine, right? So what do I subtract? Yeah, subtract 11 over 25, right? So we know what 1 minus 11 25ths is?
14, 20.
Yeah, it's gotta be the rest of the 25ths. 1 minus 11 25ths is 14 25ths. And then what do I have to do to solve for cosine?
Square root.
Now, remember, when I take a square root, what do I have to put down?
Absolutely.
No.
Yeah, which
Do you guys know? Have we done this yet? When you take a square root, what must you put down? Plus or minus? So let me show you again. What do I square to get 9?
3.
3.
Or?
Negative 3.
-3. So if I take the square root, if I do not put plus or minus, I don't get both answers. So when you are the one taking a square root, you better put plus or minus to cover your ass. Right? So cosine theta equals plus or minus. What's the square root of 14? I don't know. What's the square root of 25? Okay. Now which one are we going to choose, of course? Because we're in the second quadrant, we already told ourselves cosine's supposed to be negative.
So therefore we have the negative answer.
Negative rad 14 over 5. That's what cosine is. How would you get tangent? You could do really silly things. Here's the really silliest way to get tangent. You ready?
Oh no.
We know cosine, right?
Sine divided by
We know
We know cosine, right?
We know sine, we know cosine, we know.
True, that's the smart way to do it. We know cosine, so don't we know secant? What's secant theta? What's secant theta?
Rad 14 over 5.
Yeah,
Rad
5
14.
divided by 14, right? Negative rad 14. Couldn't I plug that in here and solve for tangent? Now that's crazy. Don't do that shit. Like somebody over here is trying to tell me, Jeff, what's tangent theta known to be in terms of sine and cosine? What's tangent theta in terms of sine and cosine?
Sine divided by cosine.
Yes, tangent theta is sine divided by cosine. Don't we know sine and cosine?
Yeah.
Now, real quick, can you guys see this? If sine theta is rad 11 over 5, and cosine theta is rad 14 over 5, negative. When I take the ratio, won't the over 5s cancel?
Mm-hmm.
So I get rad 11 over negative rad 14. And what do I have to do with that? I have to rationalize this. Multiply by the square root of 14. And I'll get square root of 154, I believe,
Doesn't cancel.
over negative 14. If you know sine and you know cosine, you know tangent. You just gotta make the ratio. That's the beautiful thing. So in all actuality, once you figure out sine and cosine, you don't have much work. You can just build the other ones off of those. How you guys feeling? It's a lot of people I never want to play poker with.
Following through.
Huh?
Following through.
Okay. Now I told you I was going to show you 2 ways to do this problem. One way to do this problem is by directly using the identities. These identities, if I know sine, I can use it today and figure out cosine. If I know cosecant, I can throw it in here and figure out what cotangent is. Do you guys see that?
Yeah.
That's an immediately useful thing to use these for. But let me show you a different way to do the same problem. This is the way I would do it, to be honest.
I drew a triangle.
Can you draw the triangle this represents?
Yeah.
Which side would be rad 11? And how do you know?
The y axis.
Why is the y-axis rad 11?
Because it's sine.
Because it's sine. Isn't sine defined to be y over r?
Yeah.
So this is rad 11, this is 5. If I want to know cosine, what side do I need?
You need the x
X side. How do I get it?
Pythagorean theorem.
So 25, 5 squared minus rad 11 squared equals that side squared.
That's right.
Oops. So b would be square root of 14. That sounds familiar, yeah?
Would be negative rad 14.
Yeah, and in this case it'd be negative, that's where we come in with the second quadrant. But let me show you, what I would do is, I know second quadrant, that's the last thing I would worry about. So when I go to make my cosine, it would be rad 14 over 5, and then I'd say, oh, I'm in the second quadrant, cosine's negative. Do you see how that's actually kind of nicer? You can agree with me or not. Either way, you got two ways you can do this kind of problem. And then tangent, same idea, just make the ratio. You know it's negative because it's in the second quadrant. Okay, maybe. So what about this very last problem? That is our first identity verification. Oh shit. So this is an identity, meaning it's always true no matter what theta is, right? Sort of like 2x plus, let's see, 2 times x plus 1 equals 2x plus 2. That is true no matter what x is, right? It's just distribution. How the hell, okay, what's the only things we know at the moment about how cosine, sine, and all that kind of stuff relate to each other directly would be these identities that I wrote somewhere. There they are. So we know these things are true. We know these things are true. This starts off with a cosine squared and a sine squared. What's happened on this side? What left? Cosine squared went away, right? And do you see how I have two of these suckers now? So listen, if sine squared plus cosine squared is 1, what is cosine squared? What do you get when you solve for cosine squared? Subtract. What would you subtract the cosine by itself? Sine squared, right? If sine squared plus cosine squared is 1, cosine squared is 1 minus sine squared. Nothing amazing there. Yes? If 2 plus 3 is 5, then 3 is 5 minus 2. That's all I said. These two add to 1, so 1 minus one of them is the other one. So wherever I see cosine squared theta, if I wanted to, I could replace it with 1 minus sine squared theta. What happens when we replace this with 1 minus sine squared theta? So that's this, and there's still this is here. What does that become? 1 minus sine squared minus another sine squared is 1 minus 2 sine squared. That's the side. Check. Crazy shit. Okay. Craziness. Is that all right? So again, watch. I want you to see. If you look at this, doesn't one side have cosine and the other one doesn't? That gives me a hint. Oh, I want to replace cosine with something else. Because this side doesn't have a cosine. So it must have been replaced to get to the other side. So then I replace cosine with something with sine. Oh, there we go. So you can use both sides to kind of give you hints as to what part to rewrite, what part to get rid of somehow. Yeah. Okay. You all excited about that? Okay. All right. So that's, I said chapter 1 practice, but it was just parts of chapter 1 there. Any questions from that paper before I get back in?
So, for that number 2, did we finish solving it?
Number 2,
Yeah, the one we just did.
Oh,
the
yeah.
cosine.
prove that this
Oh.
equals that. So see how I can make a path from this? From this, I can make a path to this.
Oh, okay.
So we prove that that equals that.
Mhm.
I love it.
Mhm.
Kick ass. Okay. So, we basically just finished chapter 1, so here's some exciting news for everybody. Oh crap. We're going to have a quiz on chapter 1 next no. What is today, Wednesday?
Yeah.
Yeah.
Next Wednesday, I'll say. Should give you plenty of time to get the homework for that done. So pretty much, remember the thing about 2 classes after I finish lecturing, you should be ready to turn homework in? That's when I schedule quizzes. I'm never going to give you a pop quiz. I'm always going to tell you Ahead of time. Okay. So now you got time to focus on getting that homework done. So you're more ready for that quiz. Okay. So anything left over from that handout or from any chapter 1 homework you guys have tried so far? Before we get into chapter 2.
I did have a question, for the homework.
Yeah.
I think it was a 61 and 62, which I think would have been, what is it?
You remember what section?
That I do not remember now. But it said like x equals 0.
Oh, here.
Yeah.
All right, let's see what this is all about. All right, so let's see, what does it say? Sorry. So there's the problem, and it says an equation is given. Oh, all right. Yeah, okay. Good. I'm glad you're saying this because I almost forgot to tell this. Here's something really interesting. So, let's say I have a triangle that looks like this, right? You with me? Let's say the angle is here. So in this case, this would be like the y piece. Is that cool? If you have to look at it like this, are you with me? If I take this side and smoosh it, smoosh. So halfway through the smooshing process, now it looks like this. You can do it, Jeff. Can you? I don't know if I can do it. Yes, you can. Swoosh! Did sine get bigger or smaller? Actually, let me be careful about it. Yeah, it doesn't matter. Let me put the angle. I can't remember exactly the way this is. Let me put the angle here real quick. Okay, so this is sine, this is cosine. Sine, if I rotate this, doesn't it get taller? Let's see if you guys are really with me. If I just rotate this, doesn't it get taller?
Yeah.
You guys see that? Because it stays the same length? Did the sine just get bigger or smaller?
Bigger.
Because the y side is bigger. The hypotenuse is the same length, correct? So if the, I don't know if I want to make numbers for this. Whatever this side is, it's a little smaller than this side, correct? The hypotenuse is always the biggest side. What if I smoosh it all the way? Bam! So the triangle's just flat, right? Is there x piece anymore?
No.
No. So cosine, and what angle, let's talk about this angle, this makes it easier. This angle is actually the same as that angle. I don't know if you guys are cool with that. It's a little bit of geometry stuff. What angle is it if I smoosh it all the way up? What angle does this become? No, this angle, if I smoosh it all the way up, becomes 90 degrees. So at 90 degrees, is there any x piece left? What'd you just tell me? Is there any x piece? Is there any x piece left?
No.
So that's 0. Sine of 90 degrees. Isn't this the y side, yes?
Yeah.
And this is the r, yes? If I smoosh it all the way in, this is still r, isn't it? This is r, but it's also y. This is weird because there's no triangle there. There is, but it's flat. Are you with me? So the cosine is 0 because there's no x at all left. I've smooshed it out of existence. It was big, smaller, gone. The y side now has gotten as big as it can be. It's equal to the radius. And isn't sine y over r? So that would be 1. Now how does that relate to this question, Jeff? That's all nice and good. Does anyone know what this is the equation of? Can somebody tell me x equals 0? Give me a point where x is 0. Any point where x is 0. Any point where x is 0. Say again. 0, 3. I love it. So here's 0, 3, right? Give me another point where x is 0.
0, -3.
0, -3. I like the way you said that. Okay, there it is, right? What would be true about every freaking point where x is 0? It would be on the y-axis. So x equals 0 is the equation of the y-axis. So what's the equation of the x-axis? Y equals 0. Okay. Kick ass. Because give me a point on the x-axis. Choose 0. Negative 4, 0. What's true always? Y is 0. That's the definition of the x-axis. So this would be y-axis, y greater equal to 0. So what that really is a triangle that they smushed to be a straight line. That is one of the weirdest problems in this little section, because there really isn't a triangle. There isn't. But that means that everything is an extreme. It's all y. Who likes y? Who likes y? I mean, between the tree. I love you guys. You guys are all like, I like z, dude. The third dimension. I mean, amongst the sine and cosine, who likes y? Sine. So if I'm on the y-axis, sine's going to be the biggest because he loves it there. Cosine likes x. If I'm on the y-axis, there's no x piece. You guys kind of with me?
Mm-hmm.
That is the weirdest question in this section. I agree. And it's really, it still is weird probably, but I don't blame you.
And the next one is just as weird.
Which one?
62.
That's just the reverse, right? You with me? Yeah. Now it's just on the x-axis, so now everything's x, but it says x less than 0, correct? So it's back here. So let me ask you guys, is there a, I forgot which way you point. Is there a y piece to this triangle?
Yeah.
Is there a y piece to this triangle?
Yeah.
Yes. Is there a y piece to this
No.
triangle? You can think of it as a failed triangle, poor little dude. So it's all x, correct? But x is negative. So sine likes y. What angle is this, by the way?
180.
Sine likes y. There is no y. So what's sine?
0.
0. Doesn't like it there. It's all x. So the hypotenuse equals the x, but the x is negative. So what's cosine going to be? Negative 1. These values being what they are will make more sense after we talk about the next thing we're going to talk about. I like the fact that they're trying to make you think that's weird. Because they're saying, what's true about this triangle that's not a triangle? And you're like, I don't know. But do you understand this idea of smooshing it flat? So right before it becomes flat, x is got tinier and y is bigger. So when I make it flat, x is 0, so cosine 0. And y equals r. Everything is on the y-axis. So the sine is 1. Same thing here. X equals r, except x is negative. So when I make cosine, it'll be negative r over r. That's negative 1. Yes.
So, whenever sine or cosine is like a multiple of 90, it's going to be 0?
I love it. Yeah. So at 0 degrees, that is all which axis? At 0 degrees, what axis is this? X-axis. So who's not going to like it here? The one who likes y. Which is that? So what's sine of 0? 0. Doesn't like it here. There's no y piece to this. If I pull my arm up a little bit, isn't there now a triangle here?
Yes.
Isn't there now a y piece?
Yes.
If I push it back down, 0 y piece. Sine is 0. Pull it up a little bit, maybe 10 degrees. Oh, now sine exists. Sine is bigger than 0. Sine is bigger. Sine is bigger. Sine is stupid big. Do you guys see that? We're getting there. I don't know if you guys, some of you guys might have seen a little trick before. This is kind of like living in the unit circle. We're going to see that in a bit. If you have no idea what the hell it is, we're going to see that in a bit. Okay. What I want to do...
So sine probably hates analog clocks then, huh? And sine and cosine probably hate analog clocks then, huh? There's 2 points where they would equal 0.
Yeah, there's some joke in there about a broken clock is right twice a day or something, but
Yeah, something like that.
something like that, yeah. Yeah, so there's times when they freak out, for damn sure. All right, so I want to do... We keep talking about triangles, and I give you the side links, but I haven't given you angles yet. So for example, if I draw a 3, 4, 5 triangle, every single one of you can tell me what the sine of A is. Can any of you tell me what A is? How big is angle A? I don't know. Shit. So we're working towards that. So to step in that direction, I want to get more specific about what sine and cosine are at certain angles. They don't even have to live in a triangle, but I can kind of start there. So let's start with a really nice triangle. Do you guys know different kinds of triangles? Yeah. What's one kind of triangle? Isosceles. What's true about an isosceles triangle? It's got two sides that are equal, which means the base angles are also equal. So isosceles. Who's got another one? Say again? Right triangle, of course. Kick ass. The monster beast of the triangle world. Right triangle. Up. Okay. You can have a triangle with a larger than 90-degree angle in it. Scalene. So the triangle is just all funky. It's got no right angle in it or anything. Right. What about the one that's got all the same side lengths? What's that called? Equilateral. I love it. So let me let me do my best job. There's an equilateral. So you work out, these are your lats, and they're equal sides, equilateral. Can anyone tell me what all the angles are? You know this. Why are they? Yeah, all the angles add to be 180. They all have to be the same because all the mouths have to open the same amount. So they all must be 180 divided by 3. 60. 60. All right, let me stop for a minute. You guys all with me? So this sucker just exists, right? So let's do this. Let's say that every side is 1 long. That is a possible equilateral triangle, right? I could have made them all 10 or 100. Who cares? Anything. I could have made them all X, but no, I'm going to keep it nice and real numbers. Okay. Is there a right triangle there somewhere? Yeah. There is. I could make one. Yeah. The simplest way to make a right triangle in there is just to drop a line from the top. Are you guys with me? Mm-hmm. What is it going to do to this angle if I do that? All right, so let's just draw the right side of that by itself, right? Because we only know shit about right triangles, correct? At the moment. Later this semester, we're going to know about any kind of triangle. It doesn't have to be right. All right. What's this angle again? 60. Still 60, right? No reason it changed, but what's this angle now? 30. And this was how long? 1. Can anyone tell me how long this is?
1/2.
Chop 1/2, exactly. Because it's symmetry, so it goes right in half, right? Do we know how long this is?
1.5.
Come on, you guys are better. What kind of triangle? Right triangle. Do I know 2 sides?
Yeah.
I love it. Do we know 2 sides? Can we figure out the last side?
Oh, 1/2
Yeah.
round 3. 1/2 round 3.
Do it. How do you figure out the last side? I know there's a fraction. We're better than that. We're the humans. We made them up. We control it. Figure out what that last side is, please.
Isn't it always extra at 3? Isn't it always extra at 3?
Extra at 3. What do you mean?
X rad 3.
Oh, yes. Well, if I made them X. I was thinking about making every side X, but no, I figured I'll just go with 1.
Yeah.
Because then it fits into the unit circle later. Yeah. So let's see, it would be 1 squared minus 1/2 squared equals whatever that side is, squared. So what's 1 minus 1/4? 3/4. If I take a square root, and I'm going to pick the positive one because this is a physical triangle. Are you with me? Okay. What's the square root of 3?
Rad 3.
Yeah, I don't know. What's the square root of 4? 2. So this is rad 3 over 2. Do you all understand? I really need you to understand. And this is why I should have maybe put X's here. If I would have put 10, 10, 10, these all just would have been 10 times as big, correct? So any ratio I would have made would reduce to the same damn thing we're going to get right now. Can anyone please tell me what the sine of 60 degrees is? Don't overthink it. Right triangle, correct? Right triangle is the angle in the base I'm talking about. All right, what's sine go? How's it go? It's the what side over the what side? Y side divided by the
R.
R. So what is it? It's rad 3 over 2. This is a fact. This is a fact. This is just a fact. That is what sine of 60 degrees is. Period. And again, if I made this triangle bigger, all these would still be 60. The sides would be each bigger, but by the same multiple. So it would reduce to this no matter how freaking big the triangle exists. Which is why we consider 60 to exist by itself. It doesn't have to be in a triangle, because whatever the hell triangle it's in, it's going to reduce to be the same damn thing. So sine of 60 just is rad 3 over 2. If you do sine of 60 in your calculator, let's see. So I'm in degrees. If I do sine 60, I get something gross, yes? Now if I do square root of 3 divided by 2, it's the same number because they're equal to each other. You understand? So sine of 60 is rad 3 over 2. Now, what is sine of 30 degrees? Yeah, now you got to do this, don't you? Right, now the angle's in the base would go this, so now this is the y side, that's 1/2. What's cosine of 60?
1/2.
Yeah, 1/2. And what's cosine of 30?
Rad 3 over 2.
Rad 3 over 2. I love it. Okay. Okay. This is just laying some groundwork. I'm going to give you a really cool way to memorize this, because yes, you will need to memorize sine of 60, sine of 30, sine of 45, sine of 90, sine of 0. Yeah, Jeff, that sounds great. Okay. So let's do one more triangle, and then I'll show you a really kick-ass way to memorize these things. Well, let's see if I have enough time. What time is it? Jesus Christ, it's already. Oh, shit. Time flies. All right, so maybe I won't do everything I just said, but we're going to look at one more triangle. Another triangle we could look at is actually already a right triangle, which is nice, but it's a specific one. It's 45, 45. Here, this time I'll use variables, just to show you. Whatever this side length is, what's true about this side?
The same.
It's got to be the same because the mouth's open the same amount, right? Can somebody take a moment, don't say it, figure out what this side is. Use the Pythagorean theorem directly, right? Math doesn't give a shit that we don't know the side lengths. We do. We know exactly how long this side is. It's x. So what's Pythagorean theorem look like? X squared plus x squared equals, we'll call this c for now, c squared, right? 2x squared equals c squared. If I take the square root, c is, careful, what's the square root of 2?
Rad 2.
I don't know. What's the square root of x squared, considering it's a real triangle, and so I got to have positive side lengths? X. Not absolute value, because like I just said, well, I see what you mean. These are already positive, so not the absolute value. Yeah. Let me stop for a minute. Okay. So are you with that? We just plug shit in the Pythagorean theorem. It almost doesn't matter what it is. We just do it, and then out comes what the other side would be. So can somebody tell me what the sine of 45 degrees is? Let me put this up here. This is x rad 2. So what's the ratio I make for sine of 45? Yeah, x over, right? Y side over hypotenuse. The x is cancel. That's the multiple. However big this damn triangle is, it would always reduce to the same number. And what do I do with this? Rationalize. Yeah. Do you see that the cosine of 45 would do the same thing?
Oh yeah.
Oh yeah. All right. So here's the ultimate cool shit. I'm gonna let you say that, Jeff. Here's something kind of crazy. All right. You ready? So if I have a circle, and I start at 0 degrees. So let me draw a few things in just to make this better. Here's 30, 60, 45, 90, right? So I really want this to make nothing but sense. This almost is too cool. Stop saying that, Jeff. You're overhyping. So do you see how the y side is bigger in that triangle? And then it's even bigger. And then it's even bigger. And then, of course, it becomes the whole thing there, right? What's the y piece at 0 degrees, though? That's when I smooshed it all the way down. What's sine of 0? 0, because there's no y piece. Sine of 30, we just figured out earlier. Did you guys write it down? I had it up here. 1/2. Do you see how sine starts off at 0, then it grows a little bit? It grows to become 1/2. Sine of 45.
Right, 2/2.
Right, 2/2. Sine 60 we did earlier.
Right, 3/2.
Do you see how it keeps getting bigger? Doesn't that match visually what the shit's happening to the triangle? Isn't the y piece getting bigger and bigger as it goes the y piece is getting bigger, right? And of course at 90, we said this earlier, it's all freaking y. This is 1. Now real quick, now watch. This pattern kicks ass. Interesting. Do you all agree with me? Real quick, that's it. That's the reality in the first quadrant for sine, correct? You guys with me? That's just it. We already proved all of that shit. Here's a way to remember this. Do you all agree the square root of 0 is still 0?
Yeah.
Do you all agree if we divide by 2 it's still 0?
Yeah.
Square root of 1 was 1, correct?
Yeah.
Square root of 0/2, square root of 1/2, square root of 2/2, square root of 3/2. So this should be the square root of 4/2. What's the square root of 4?
1.
What's the square root of 4? 2 divided by 2. 1. So it's kind of a nice way, and again, it's just, it doesn't mean that much, but it definitely is one way to kind of remember this shit. So what does cosine do? Cosine lets x, so it's going to start at 1 here. Do you see how this x side is shorter, and this x side is shorter, and this x side is shorter? So cosine is just going to do all this in reverse. Do you see that? Sort of. So there are triangles that I can relate these to, but they don't have to relate to triangles. Sine of 30 is 1/2.
Yeah.
Period. Yes?
Can't you also remember as the x values grow, the y values also decrease?
Yeah, as the x values get bigger, the y... Yeah, sure. Yeah, there's a multiple different ways to remember this. I'm going to kind of tell you the way I remember it, but there's a lot of different ways to memorize this stuff. Yeah.
Isn't this like the unit circle?
Totally. I just didn't call it that. So how big is this radius assumed to be? 1. And that's why we call it the unit circle. What kind of number is 2? It's prime, right? What kind of number is 15? It's composite. Do you guys remember this? What kind of number is 1? It's not prime or composite. It's the unit number. So we call this the unit circle because it's a circle with radius 1. You guys with me? A little bit? Okay. All right, that was a lot. And that's enough. I think that's where we end, yes. Okay, so don't forget, quiz a week from today. We're going to continue going in chapter 2. We just got into chapter 2, by the way. That's where all the stuff was from. We'll continue with that next time. If you have any questions, come up and see me. Otherwise, I'll see you guys. Have a good weekend. Robert? Yeah. Oh shit. Okay.